Hello everyone, welcome to today's webinar where we will be talking about HV underground lines. And before we start, let's just wait 1 or 2 more minutes for everyone to join. And while we are waiting, just to present myself, um, I'm Álvaro Benito. I'm an electrical engineer at RatedPower. I've been working here for around 4 years already in the product team as an electrical engineer and software developer for the interconnection team. And also, as a reminder, you have access to all the webinars in our ratedpower.com website. So here in the resources webinars, you can have access to the upcoming webinars. This is today's. And the next one will be about driving the solar and storage integration in CNI projects across MENA, together with Solis Depot. So this will be very interesting, I believe. So yeah, feel free to join this. And without further ado, let's begin with today's webinar. So this presentation is divided into 5 chapters. First one is the introduction. What is an underground cable and its components. Then a comparison with the overhead line to understand the advantages and disadvantages of both technologies. Then the underground cable sizing. Fourth, it's going to be how we implement it in RatedPower and what results can you obtain from it. And finally, some conclusions of the presentation. So for the introduction, first let's just do a small definition of what an underground cable is. Basically, it's an underground transmission line. Is an underground electrical cable used to transport electricity from one location to another, and it serves as an alternative to the traditional overhead lines that we have had for transmission purposes. The different components of a transmission underground line, there are not too many. It's just the cable, the terminals, and the joints. The cable is a bit more complex than a conductor from an overhead line, in which you only have the electrical conductor. Here you have different layers. So you have the conductor, the copper or aluminum. Then you have shields, and the objective of the shield is to create a more even electrical field around the conductor. This way we avoid having partial discharges. If we don't have this shield, we might have a voltage gradient due to the air gaps, and these voltage gradients might damage the insulation. Then we have the insulation, which isolates the conductor from the exterior. The metallic sheath, which provides an electromagnetic shielding, and it also gives mechanical support to the cable. And finally, a jacket which protects the cable from the outside. So, for example, from humidity or external elements. Then the terminals are two electrical components that are placed at the beginning and at the end of the transmission line to connect the transmission line with the substation. And finally, the joints. These elements are used to connect different cable pieces. Let's say, for example, you have a 10-kilometer transmission underground cable. You're not going to have just one piece of cable of 10 kilometers. You will have like small pieces of 500 meters, and you have to connect these small pieces to form the bigger transmission line. And you connect them using these joints, which are elements that have to fulfill certain requirements of connectivity between the two pieces. They also need to be able to protect the cable from the external humidity, for example. And both these terminals and joints, they must be sized according to IEC 6840 and IEC 62067. And then before jumping into the comparison with the overhead lines, why are we now all of a sudden using underground cables for transmission line purposes when historically we've been using overhead lines primarily. And the reason why we're doing this is because we lack space for more overhead lines. This is especially true in countries, for example, from Europe. So in France, Germany, Iberia, in the UK, we have a lack of space for overhead lines. So the only available option is underground cables. This is also like it not only happens in Europe, it happens all over the world, in Asia, in some countries, like Japan, in the US, in certain areas as well, in LATAM as well. So all over the world, this is happening, that we don't have space for overhead lines. And we're gonna see now, talking about overhead lines, the comparison between the underground buried cable and the overhead line. So the main difference and the most important one is the cost. The reason why we've been going for OHL primarily historically is that it's way cheaper. And here you have a comparison made by the IET, the Institution of Engineering and Technology. They made this study called a comparison of electricity transmission technologies, in which, well, it's very deep. I'm just taking a few pictures from it, but they compare the different costs between different transmission line technologies. And in this case, for example, this would be the cost of a 75 kilometers and 5 gigawatts transmission line. And you see here that the difference is that the underground cable is 4.68 more expensive than the OHL. So, right, just watching at this, it looks like the OHL is the go-to solution if there's no other requirement that forces us to go for the underground cable. Here we have another chart from the same study in which it compares the different lifetime cost for the OHL and the underground cable per megawatt and per kilometer. And you see here for the overhead line, you get like 1.2k euros versus the 5.7k euros for the underground cable. So yeah, economically, the OHL is way cheaper and way better solution. Then we can compare different behavioral aspects of the OHL and the underground cable. So for example, the environmental impact, the initial impact of the OHL is way lower because you're just placing a few towers. And for the underground cable, you have to dig all the trenches throughout the entire path. Then in terms of weather exposure, the OHL is exposed to lightning and harsh weather conditions, whereas the underground cable is just exposed to potential flooding. However, this overhead line exposure we've seen historically that is not too much of a problem, and there's not that many issues because of this weather exposure. Then the big one is the visual impact. The overhead line is something that we see there. The underground cable, however, is below our feet, so we don't even realize that it's down there. And then in terms of reliability and maintenance and accessibility, overhead line is just superior. It's way easier to access it. For the underground cable, it's harder to locate a fault. You need to dig in the planes where the fault happened, so it's way harder to maintain. Then if we go to the electrical behavior, we also see differences, even though it's just two pieces of cable, one is overhead and the other one is underground. They also behave differently when we check out the electrical characteristics. So one of the main differences is the capacitance of the cable. So for overhead line, we have lower capacitance, and for underground cable, the capacitance is way higher. This results in the necessity of having shunt reactors for long distance underground cables, increasing the costs and also increasing the design complexity. In the inductance, the behavior is different. So all the way around, the inductance in the overhead line is higher, causing more voltage drop, but this is not something very noticeable. For the underground cables, it's lower, and also having lower inductance means that the transient behavior during faults is a bit worse because the peak current during these faults is slightly higher. Then for thermal behavior, overhead lines have better heat dissipation due to the air having like dissipating heat better than the ground. As we mentioned before, the faults are easier to locate in an overhead line. Then another electrical behavior which is different is the surge impedance of the overhead line, which is way higher than the one of the underground cable. This means that the transient behavior of the overhead line is slightly better. And this surge impedance, I won't go too deep into what it does, but it's very useful for wave propagation during faults. And finally, the corona effect, which is something that is bad for the overhead line. This corona effect is present at high voltages and basically produces losses in the overhead line. This is due to the ionization of the air around the conductor, and this effect is non-existent for the underground cable because of the shielding. So we checked that overall the overhead line is a better solution unless we don't have the option to build it. So now let's go to the underground line sizing. So the easiest way to size an underground cable is through these three criteria: the current carrying capacity criterion, the voltage drop criterion, and the short circuit criterion. The current carrying capacity is basically how much current can our transmission line withstand without reaching the cable's thermal limit. This thermal limit is typically defined by the insulation used. So for example, for XLPE insulation, the thermal limit would be at 90 Celsius. Then the voltage drop criterion, which reflects how much voltage drop is admissible to have in the transmission line. So typically values of 5% are used. So more than 5% voltage drop would not be ideal. And finally, the short circuit criterion, in which the transmission line has to be able to withstand a short circuit fault of a specific magnitude during a specific fault time. So jumping into the first of the criteria, current carrying capacity, the way to calculate this is fairly simple. First, we have to compute the operating current based on the apparent power of the line and the voltage of the line. Then we will apply some correction factors. These correction factors are based on the lane depth. So a deeper cable will have worse behavior. If the ground temperature is higher, again, worse behavior of the cable. Also, the thermal resistivity of the ground is something to take into account. And finally, the distance between circuits and other groups of circuits that might be around. Then, based on the correction factors, we update the nominal current. And we have to compare this corrected nominal current with the maximum admissible current from a database of conductors. So typically, for example, these are from ABB. Typically, they will provide a set of cables and the maximum allowed current of these cables. So we just pick the cable that fulfills our current carrying capacity needs. For the voltage drop, we have this small formula right here. This is the typical voltage drop formula, in which considering the electrical parameters of the cable, the resistance, reactance that we have in the database as well of the conductor, and considering the nominal current, we can calculate how much voltage drop we would have in this transmission line. And this voltage drop will have to be lower than the limit that we defined. Similarly, for the short circuit current, we have a small formula right here. By the way, all of this information, you can find it in the methodology of RatedPower, the transmission line underground cable methodology. So yeah, going back to the short circuit current, this formula basically computes what is the minimum section required to withstand this specific short circuit. So this short circuit will have a current. This current in the software in RatedPower we estimate it based on the voltage of the line, but it could be calculated more precisely based on the network that we are connected to. Then for the time of short circuit, we consider 1 second fault. Then we have some constant depending on the material, whether it's aluminum or copper. And finally, the initial and final permissible conductor temperatures, which are based on the insulation used. And now let's move on to RatedPower software. So how does the underground cable, how is it sized in RatedPower? So this was released a few months ago, this feature in which you can define an HV line, an HV underground cable in the software, and then automatically we will calculate, do a preliminary study, calculate the ampacity, all of this criterion that we mentioned, and size this underground line. So the first thing is to define the path, the HV cable path in our site that will go from the substation to wherever we want it to go. We can define the trajectory in our site creation tool, and then we can click on save. We can name the site and click on save site, and this will automatically upload the site that we have in the site definition menu. After the site has been uploaded, we will go to the design process tab where we can define the different inputs for the HV line. Now for the inputs definition, we have several inputs that we can play around. The first one is the cable formation. So for the cable formation, we can either define a trefoil or flat formation between the conductors. Then for cross sections, we have a list of possible cross sections for the conductor. Then we can define the maximum circuits per phase. This doesn't mean that we will choose always 2 circuits. It means that we can choose either 1 or 2. The software will do it automatically. Then the material between aluminum and copper, the depth of lane between 0.5 and 2 meters, and the distance between the circuits. If we have several circuits, then we can define the maximum voltage drop of our design. The software will automatically select a section that fulfills this maximum voltage drop requirement. And finally, we can click on Run Design, and the simulation will begin to run. And after the simulation finishes, we can access the results. So for the results, first we generate a set of documentation. You can have access to the AC model in raw format file, to the bill of quantities, and to the listing of cables. And once you select them, you click on download, and the different documents are downloaded. This is the bill of quantities in which we will showcase the different conductor, joints, terminals, the screen cable, and the civil works, the trenches. We will define the units and the quantity. Then for the listing of cables, we will have different sections for MB, string box, string cables, and HV cables in this case, in which we will include them with the circuits, cross-section length, the power voltage and voltage drop, the load current and the maximum allowed load current, the cable's temperature, short circuit current, etc., trenches. So all of the information that we compute internally will be placed into this listing of cables, like all of the correction factors that we mentioned previously, for example. And finally, the electrical parameters, so resistances, reactance, zero sequence parameters, and capacity susceptance. And then we have the raw format file, which can be imported into external software such as PSSE or DigSilent. We will create a specific bus for the HV cable and the branch, the line from, in this case, buses 18 and 19. So we will create a transmission line, and this will be able to be exported to external software for power flow analysis or short circuit analysis. And finally, if we go back to the software, we can see in the results section that we have a brief summary of the HV underground lines results with some of the parameters and the voltage drop. If we have several HV underground lines, which is something that we can achieve by having more than one substation, we will also have access here to each result of each underground cable. Now some considerations that we do internally in our calculation model. First, we consider always cross-bonded cables. These are best suited for long distances and for HV cables. They are very good because they have some advantages, which is that they produce less induced voltages, lower circulating currents in the sheets because we are compensating the magnetic field, and then improved cable ampacity because due to these lower circulating currents, there's also less heat. So there's a slightly higher ampacity in this cross-bonded bonding configuration. Then for the formation, which can be flat or trefoil, depending on the user definition. For the flat formation, we define a spacing of 70 millimeters between the cables within each circuit. So they will not be stuck one to each other. There will be a small spacing between each other. Then the insulation, we always use XLPE. For the losses, we consider both Joule and dielectric losses. So current dependent and voltage dependent losses. Then the joints, we install them every 500 meters. We found that this to be a typical approach. And finally, a clearance of 50 millimeters is always maintained between both sides of the trench and the cables. This small clearance is for the installation to be properly done so that the cable can be correctly installed within the trench. And now let's jump to some conclusions of the presentation. First one, we checked, we saw that the underground cables have higher cost than the overhead line in general. And the only reason or the main reason why we would go for underground cables for high voltage transmission lines is that they are the only available option in certain countries. So if there's the option of an overhead line, I think it's the go-to solution. If not, we have to deal with the fact that we need to have an underground cable. Then we also saw that both underground cable and overhead line have different electrical behavior, even though they are just a cable that goes from point A to point B. And this is mainly because of the distance between the conductors and the place where they are installed. Then we saw that for sizing the electrical underground cables, we just need three requirements: the current capacity, voltage drop, and short circuit. There's also one criteria, which is the electromagnetic study, but we don't cover it in our software. And for preliminary designs, this is not really that important. It must be done later on. And finally, we saw that RatedPower software provides the necessary tools to run a preliminary design of an underground cable, giving enough documentation for this stage of the project. Yeah, those are the main conclusions of the presentation. So thank you all for coming here. And now let's open the questions, the Q&A session. So feel free to drop your questions in the question box in the webinar menu, and I will be happy to answer them. And I see already one question, which is, are you considering the proximity and skin effect for the resistance calculation? So yeah, we take the DC resistance from the manufacturer, and then we apply the proximity and the skin effect to this resistance to translate it to the AC resistance of the cable. Okay, we have another one. How do we take the HV line into design consideration, as many factors are unknown before actually physically being on site to confirm? So yeah, there's always the problem of on paper everything is feasible, and then once you get there, you suddenly start to realize that you cannot build the line through this path, or you have to do another path. Typically during designs, you will have several paths, and you want to iterate fast and to have preliminary designs on those paths. So for these automated tools, like RatedPower, for example, can be useful. You have always to do an on-site study on like hydrological considerations and things like that. So that's something that you cannot skip. So yeah, at this point, the important thing is to have a preliminary design, to have different options, different alternatives, different um, trajectories, and then during the project, more deep, like a deeper engineering analysis, you will have to deal with with these nuances. Okay, so we have another one. Hello, can we calculate DC-HV cables? We don't have that option yet in the software. For this, we would also need to have the engineering to have the HV transformers, the DC-HV transformers, to have like high voltage DC power. And this is something that we don't have yet. So no, the answer to that is not yet. Okay, I don't understand why the fact of installing undergrounded is because there is no space for HLs. Can you develop this idea? Yeah, so basically, well, historically, the underground cables were installed near urban areas, and this is still being the case. But for the, let's say, for the not non-urban areas, typically we would just install overhead lines. The problem is that even though we think that there's a lot of space for them, there's not really that much space. Governments also don't want to have as many overhead lines because of the impact in the natural habitats and the yeah, the ecological impact. So yeah, I mean, probably there could be more space for overhead lines, but there's also like a political approach here. And yeah, many times we think there's more space than there's actually in the sites that we are developing at. There's a minimum voltage level in the software to consider the underground line an HV line. Yeah, so we have, let me just go here at the connection type. Okay, so this is the software right here. So in the grid point, we have the MV level and we have the HV level. If you put here 1 kilovolt, the minimum voltage is set to 46 kilovolts. So this is the minimum voltage that you can have for an HV underground line. You can also have MV underground cables, but if you have a substation, you will have and you want an HV cable, the limit is 46 kilovolts. Okay, and I think that's very much it. If there's no more questions, let me just refresh this. Okay. So yeah. Okay, so if there's no more questions, I think we can close it here. Thank you everyone for attending. Thanks for coming. If you have any questions, feel free to email me or anyone in the team. See you in a future webinar. Thank you.